All right, so SSDs are a big improvement on hard drives. And they're a big improvement because they're going in a direction away from mechanical devices that have latency limitations towards acting like the thing that programmers would like to deal with, which is kind of like DRAM, the random access memory that you use for storing non-persistent data. Except you'd like it to be persistent, but other than that, you'd prefer to have something that's just like DRAM. You want it to be byte addressable, which means that you don't have to access blocks. You can just give it an arbitrary like 64-bit memory address and a size, and it will give you back some data. Or maybe you don't even have to give it a size because you can just work with it through pointers, like memory mapping, but with no translation layer in the middle. You want it to be fast, and it's important that we don't have endurance limitations. The endurance limitations on SSDs are almost as awkward from a sort of design perspective as the latency limitations and the fact that hard drives are mechanical for hard drives. Endurance limitations mess everything up. And so that's what we like for our ideal persistent storage or non-volatile random access memory. And it kind of looks like we're going in that direction. There's been a lot of research on that, and a lot of progress has been made on making progress on sort of getting that stuff out of the lab and turned into products. And the biggest example of that we've seen recently is a product from Intel, or a product line from Intel called Optane. This is a new kind of persistent non-volatile memory. The sort of technical marketing term that they're using for the technology is 3D crosspoint with an X for cross, and it was developed as a collaboration between Intel and Micron, who are a big memory manufacturer. And it's getting closer to this ideal NVRAM ideal than NAND flash is. Unfortunately, the actual products that they've released haven't been the most breakthrough thing ever, and there's a couple of limitations that they have. The first limitation is that the first product that they wanted to release was Optane solid-state drives. So you can just drop them in place of a NAND solid-state drive, and they didn't even bother releasing SATA versions of Optane drives because the restrictions for the SATA interface, which was designed for hard drives, would have just killed any performance benefits from Optane. You wouldn't have been able to tell the difference between Optane and NAND flash on SATA. So they're targeting NVMe, but even with NVMe doesn't go quite far enough as far as supporting things like byte addressability, because that's not what they were expecting to have to deal with. And so if you get a solid-state drive that's built using this 3D crosspoint called Optane from Intel, you're going to get a solid-state drive that acts a lot like a NAND solid-state drive, except it has one pretty clear benefit, which is that you can do more I/O operations per second. That's one of the things that people like to benchmark with SSDs. And it's not quite the same as throughput speed. You can't send more data to the disk faster or read more data back from the disk faster. It's actually just random operations that sort of show this thing. And it's less a question of sort of bandwidth sending things back and forth, and more a question of whether or not it has to deal with queuing in various ways. But the result is that it is a limitation in NAND-based solid-state drives, and it's less of a limitation in Optane-based solid-state drives. The other super unfortunate thing about Optane as a technology is that it still has an endurance limit. It's not as big, it's not as immediate an endurance limit as NAND flash. It doesn't seem to scale in quite the same way that as you make your flash SSD denser, you have to do this SLC versus QLC trade-off, where denser disks with larger capacities have even worse endurance than the older disks. But there still is an endurance limit, and so Optane probably isn't the ideal NVRAM that we're going to want in the long term. But Intel did release another product in addition to their solid-state drives, and that is they released Optane in the form of DIMMs, which is the form factor that we get memory chips in. So rather than plugging it into your SSD slots, you can plug it into the memory slots. And for that, what you get is memory that is significantly higher capacity than DRAM. And that's the main thing that they're advertising, is that instead of plugging in a, 32 gig DIMM, if you go get an Optane DIMM, you can plug in a 256 gig DIMM in the slot that previously would have only fit 32 gigs. And so for some applications where dealing with a large data set is important, this is clearly better. The downside, of course, there's two major downsides. The first one is that Optane is way slower than regular DRAM, like factor of 10 slower. In a DIMM form factor, it's noticeably faster than NAND flash would be, like factor of 10 faster, but we're in the middle there and we're not quite as fast as DRAM. And the other sort of bigger problem is that we still have an endurance issue. So eventually the Optane DIMM will wear out, and so you have to do sort of a careful engineering choice with your sort of software development of, do you put in this weird piece of hardware that acts differently from any normal piece of hardware that we've had in a while, and it's sort of a consumable resource for some applications. So Optane DIMMs are a really interesting advancement, but it's not clear that they're this like breakthrough that's going to change the world, except in some small areas of servers. But they are moving us more in this direction of ideal nvram. There's some other technologies that exist that we may see come out as products that will make it so that a lot of the optimizations that we've done for file systems that make sense for hard drives, make sense for flash-based solid-state drives, and even make sense for flash-based Optane won't make as much sense, especially this idea of byte addressability. Once we have byte addressable NVRAM that's reasonably fast, the distinction between a file system and a memory allocator becomes much less clear. And if you throw in like databases are also in the same bucket, maybe we'll have to redesign everything and like decide that everything is now a database, or everything is now a big hash table, or everything is now a big B+ tree. And that'll be fun. That'll give systems programmers a lot of work to do, and I'm not necessarily going to bet that this great redesign is going to happen right away. In fact, even once the hardware comes out, everybody's going to try to ignore it for as long as possible until someone demonstrates that you can get a like huge benefit on some concrete application by saying, no, we're not going to have a file system, we're just going to replace it with a hash table. But it's something that I do expect there's a good chance that we'll see over the next 20 years of computing architecture. All right, so that's an example of a technology that looks like it could be the ideal NVRAM that we want is MRAM. There's a bunch of others, resistive RAM. Hewlett-Packard had something called memristors that everybody was super crazy about. There's FERAM, which, I don't know. These are just, it's a whole bunch of acronyms, and you have to go look at the description of the technology and the progress of it to really see what's going on. But there's at least 5 or 6 candidates for an ideal NVRAM, and MRAM actually exists. It's something that you can go buy. The problem is, if you want to get an MRAM module, what they'll sell you is a 512K MRAM module for $20. And if you're building an embedded system where you'd like to design in this sort of ideal NVRAM style, that might be useful. It's not as fast as even Optane, and that's all because that particular chip is getting built on like a 45 nanometer manufacturing process that was obsolete 10 years ago because it hasn't scaled to sort of mainstream commercial production yet, and there's some bottlenecks that are preventing them from doing that, which is why I say this whole ideal NVRAM story is like a decade in the future, but we probably will see it. All right, so next topic for today, I want to talk a little bit about RAID, but that'll be in the next video. See you in a second.